Okay. So let me start. So in the last class, we were talking about microcanonical ensemble, where so how we define a microcanonical ensemble is the case where the energy remains constant, right? And then so in that case, it's a closed system. But now what we will talk about today is a canonical ensemble. So in this case, we will see that the system is not closed and it can exchange energy. What defines the system is the temperature. And we'll see that how we can derive the phase space density of a canonical ensemble and how that can be used to solve for the different thermodynamic parameters and the equation of states. Okay, so you have the basic idea of ensemble theory, right?
Yes.
Yeah. Okay. Okay. So let me get going. So uh, regarding canonical ensemble, so here the system has some energy Es, and then there's a heat bath which is having some energy Er, and then there can be exchange of energy between the two. So now, if we want to find the number of microstates, which is which defines the so we want to find the probability of finding the system S in certain microstate I with energy Ei, and that is proportional to number of microstates omega S for a particular energy Ei. Now, because the total energy of, if we consider total, like with the reservoir as well as the system is conserved, that means this is also proportional to the number of microstates for which the reservoir remains at an energy E minus Ei. Okay, so Pi is proportional to omega R Er, where Er is uh, the energy of the reservoir, or it can also be written as omega R of E minus Ei. Okay. Now, because the heat bath is very large and we can have this assumption that Ei is much less than E, what we can do is we can expand the expression in this way. Okay. What this tells us is that now, what from here, considering that E is like approximately equal to Er because it's the reservoir, so it has greater energy, we can do this assumption, and what we get is this value. This is already known to us. So from here, what we derive is this expression, which tells us that the number of microstates of the heat bath decreases exponentially with the increase of the system, increase in with the energy of the system. And then this Pi is actually proportional to minus of Ei by kT, where Ei is the energy of the system. So initially, when we were talking about microcanonical ensemble, their Pi was constant and it was given as 1 by omega, where omega is the number of microstates. But in this case, because there can be exchange of energy, now there is a weight factor that is being added, and that has a dependence on temperature, as you can dependence on energy, as you can see here. Okay, now this is the expression, so this is proportional, so the probability is proportional to this factor. What we can then do is we can use the normalization concept for probability, and that would give us the exact expression for the probability of finding um, the system in a certain microstate I with energy Ei. This is the expression for the probability density. Now, if so, this has a summation. That means here it has discrete values. Now, if we have to have a continuous system, there the summation has to be exchanged with integration. And what we then get is something like this. Okay. So you are already well versed with this expression, right? So here, this is this expression is clear.
Yes.
Okay. So here what you can now see is that this expression here, the denominator, has very significant implication. So this is called, this denominator is denoted as Z, and this is called the canonical partition function. Okay, and we will see how by just knowing or calculating the partition function, we can derive the different thermodynamic quantities from here. Okay, this is here written in terms of the continuous notation. Okay, H is the Hamilton. Okay. Now, if we know if we know the uh, probability density, how do we define the entropy? This is given by this expression here, and you can see that now here, because we are talking about canonical ensemble, we have to put the phase space density expression for the canonical ensemble. Okay, and then if you do that, what you get is something like this. Now, if you just look at the first term here, what this tells us is that now you are calculating the average of, or you can say the, yes, the average of this of the Hamilton. So that will actually give you, so this is the average. Okay, the first term gives you the average, and the second term is KLNZ. Now the average of H is actually the average energy. Okay, so in that way, S is related to the internal energy, average internal energy, by this expression here. Now we already know that, now you can just exchange it to get U minus Ts as minus KTlnZ. And we know from thermodynamics that that's the expression for the Helmholtz free energy. So that in a way tells us how one can get the Helmholtz free energy in terms of the canonical partition function. Okay, and we'll see how this is very relevant in order to find the different thermodynamic variables. What's again interesting is that now, if you look at this expression, so we already know this thing, 1 by T is equal to del S del U. This comes from thermodynamics, and we know that. But now if we use the expression for S here, from the expression that is given here, and then if we do this derivative, we get something like this. And that in a way tells us, now if you look closely at this last line of the expression, that one can directly get the average internal energy by doing a derivative with respect to beta of k, l, and z. Okay, so if you know the partition function, you can directly do a derivative. You can directly use this relation to find the internal energy. You don't have to go through the entire process of finding S, finding T, P, and all the parameters, and then using the relation. You can do that, but you can also do this. So this will give you directly the value of the average internal energy. Okay, so this is the relation that you can use, right? Okay, so now we'll see some of the examples, and we'll see how we can use our knowledge to solve certain systems, certain kind of systems. Okay. So we want to study this system of n ideal gas molecules in 3D. Okay. So because it's in 3D, we know that here we have this, so this is the momentum, and it's in 3D, so it runs from nu equal to 1 to 3n, because we have n gas molecules, right? So if you use this relation in the expression for the partition function, this is what you get. Is it clear why you have used the value of n factorial here?
For continuous perspective.
No. For continuous thing, you're using the integration. If it was not continuous, you would have used a summation, right?
For n particle for n particles.
Okay, so whenever there is n particles, do you have this n factorial there? Or does it have something else also to do with it?
Hmm, just
So if you have the Hamilton, this is the partition function. You know the expression for the partition function, right? So it's just
yes.
integration of e to the power minus beta h on the phase space. And then you divide by h to the power 3n, which comes because of the, so it comes from the minimum uncertainty that one microstate can have. So the minimum volume that a microstate can have on the phase space. This h to the power 3n is clear, right?
Yes. I think
Okay.
for uh,
Yeah, tell me.
s to the power 3, and I think I just forget, but I
So
know.
so the thing is that you you are doing an integration over the entire phase space of e to the power minus beta h. But then finally, what you want to get is the number of microstates. So in that case, what you have to finally do is you have to divide by the minimum volume in the phase space that a single microstate can have. Okay. And then we know from quantum
Yes,
uncertainty, like
yes, yes.
Heisenberg uncertainty, that del P del Q is greater than equal to H.
Yeah.
So now you
S to
have,
the power 3. Yeah. S to the power
so
3
if
n
it
is
is,
position and
tell me.
momentum. No?
Yes, so position and
Uh,
momentum uncertainty for a particular coordinate, it will be del P del Q greater than equal to
the
H. And then you have
minimum
3n
volume.
of them because 3D and n gas molecules. So from there you get this H to the power 3n. So that explains why you have H to the power 3n. Okay, because you were dividing by the minimum volume that one microstate can have. But then why do you have this n factorial here? So see, the n factorial comes because of the indistinguishability of the gas molecules. So this is called the Gibbs factor. So if you have distinguishable particles, then you can arrange them in some. No, so suppose if you have three particles and three particles are distinguishable. So in how many ways can you arrange them? You can arrange them in 6 ways, like 3 factorial ways. But then if they are indistinguishable, then just by changing their order won't change anything because all of them cannot be distinguished from each other. So then the number of microstates gets reduced. So in that case, you have to divide by n factorial. So here when you have this n ideal gas molecules, they are indistinguishable. So in that, so whenever you have indistinguishable particles, you have to divide by the Gibbs factor. But if they are distinguishable, then this n factorial should not be there. Is it clear?
Yes, yes.
Yeah.
Actually, was forget about and factorial, but now it's clear.
Okay. So now what you see here is that in the expression for H, you don't have any momentum, any position dependence. It only depends on the momentum. So that means you can take this coordinate, like the position coordinate out. And if you integrate that, what will you get? So if you just integrate integration of D3 and Q, what do you get out of that?
Volume. Uh,
Huh?
yeah.
So uh, if V is the volume, now you have 3n. So each particle or each gas molecule can be inside the volume. So if V is the volume of the container, D3Q should be equal to volume. But then you have n of them. So that means this value should come out to be V to the power n, right? Because you have n
Yes.
molecules, right? Now what we have to integrate or what is left is just this integration, which is the integration of the momentum. It has only momentum here, right? So what you then do here is that you use an identity of Gaussian integral, and this is the identity. So you do a substitution, and then what you get is something like this, correct? Here, so beta is 1 by kt, and that is how it has been substituted here. And we get to an expression like this. So this is the expression for the canonical partition function for n ideal gas molecules in 3D. Is this clear till here?
Yes, yes.
Yeah, yeah. Okay. So now this is just a simplified way of writing this expression. Okay. So what you then get from here is that you can use this relation of to find the free energy, the Helmholtz free energy, that is given as minus kT ln z. Okay. And then once you find the free energy, you know how to find the pressure. Okay, this is what you get from the pressure, and the relation here you can also get an expression for the equation of state. And similarly you can find the entropy. Okay, you can also find the chemical potential. So all the thermodynamic parameters can be obtained once you find the free energy, and that comes from the canonical partition function. Okay, and this is the expression for the internal energy. Is this clear? Okay. So what we then do is the ultra relativistic gas. So this is another problem, and we'll see how we can solve this. Okay. So we want to find the different thermodynamic properties or thermodynamic parameters of n relativistic gas molecules. Okay. And the given Hamilton is something like this. Okay. So it again depends only on the momentum. So we will see how to do that. So as you can see here, again we have taken v to the power n out because the Hamilton only depends on the momentum. But now we get an expression like this, right? So here you can see that initially the integration was about d to the power 3n, okay, because there were 3n number of momentum coordinates. So for each particle 3, and then there are n, so 3n. But then what we see here is that the Hamilton depends on the magnitude of the momentum. So what we do therefore is that we go for the spherical coordinate, and there then the product goes from nu equal to 1 to n, because now for each particle we'll consider the spherical coordinate that we are going to use. Is this clear how you get from here to here? Okay, so maybe I'll consider that it's clear. So what we then do is we do this integration, okay? Because all of them are same, so we can just do for one, and then that value to the power n will be our expression, okay? So we change to spherical
Huh.
polar coordinates and we do this
Yeah.
integration.
Hello,
And
hello.
hello? Yes.
Yeah. Don't consider I am. Just again repeat the above relation about to convert spherical polar coordinate. How to do? Yeah.
Yeah, so, okay. So, because I was not getting a response, so I thought it's clear. Okay, so,
I, I
what
just
you,
thinking and in that time.
okay. So, what you see here is that first, each of the particles will have, so they are identical particles. So, that means the integration over d to the power 3n can be written as product of in n integrations, each for d cube p, okay, because now you are doing this integration for one particle and then you have n products of them to account for the n relativistic molecules, okay. But then once you get this expression d3p, you have to, so this means d3p is similar to writing it as dpx, dpy, dpz. But what you want to do then is we want to change to the spherical polar coordinates. Why? Because you can see here that in this expression for the Hamilton, it only depends on the magnitude of P. So it's easier to solve if we change this expression, not in the form of dx, dpx, dpy, dpz, but rather write it as integration of 4 pi p squared dp. So 4 pi p square dp is something you get like integration of r square sine theta d theta d phi dr, and then you integrate. So here r would be your value of p, because that's just a expression. So here the radius actually is p. So you get, and then you integrate over the theta and phi, and what expression you get is 4 pi p squared dp. Do you understand that? So you have, so this is just similar to how you change from dx, integration of dx dy dz, to integration of 4 pi r squared dr.
Yeah.
Yeah, so that's what has been done here. Okay, and then because you have n of them, you take n product of n such integrals, and so you have to the power n. Okay, so when you were doing this integration, each of the variables dpx, dpy, and dpz were ranging from minus infinity to infinity. But once you change to the spherical polar coordinate, it will range from 0 to infinity, because now here p is the radius in the momentum space. Clear, right? This thing is clear.
Yes, yes.
Yeah. So now what you do is you take this substitution, and once you do the substitution, you get to an expression like this. So this integral is actually the expression for gamma function. So it's like 0 to infinity x to the power n minus 1 dx e to the power x is equal to gamma n. Okay. So here that means this value can be substituted as gamma 3. And then you use this relation to find the final expression for the partition function. Okay. Now, once you get the expression for the partition function, what you then do is you use your well-known relations to find the free energy and also the pressure or entropy or the chemical potential, as you have done in the last case. So if you have to find any of the thermodynamic parameters, this is how you have to proceed once you are given the Hamilton. Okay, and you can use this relation to find the internal energy as well. Clear, right? This thing is clear.
Yes.
Okay, so what we then do is we do another question where we have this harmonic oscillators in a canonical ensemble. So we want to find the thermodynamic properties of n distinguishable harmonic oscillators of frequency omega. So for harmonic oscillator, what is the Hamiltonian, what is the Hamilton it should be?
Just uh, h p square upon 2m, um, the loss of m omega square x square.
Right. So for n such particles, you'll get an expression something like this. Okay. So now here you have both the dependence of position coordinate as well as momentum in the expression for Hamilton. Okay. So that means here when you find this value, you cannot take v to the power n out. You have to do this integration. Right. And if you look at the expression, you see that we don't have this 1 by n factorial here. Why? Because in the question it's specified that it's a distinguishable harmonic. We have n distinguishable harmonic oscillators. So we don't divide by the Gibbs factor. So now this is the expression for the partition function. What we do is we do the integrations, and because they are identical particles, so we can find for one particle and do a product n times. Okay, and then what we see here is that now we have divided the integration for the position coordinate and the momentum coordinate, right? And we do this substitution to get an expression where what the relation that we use is the same Gaussian integral of minus infinity to infinity e to the power minus x square dx is root over pi. So if we use that relation, we do the substitution and we use this relation to finally get to this expression for the partition function. Okay. So once we get the partition function, we can similarly get the different free energy and the other values, right? So one has to get used to this way of solving the different solving for the different partition functions given a particular Hamiltonian, and then that would give you the different thermodynamic variables. Okay. Now we want to derive it for n quantum mechanical harmonic oscillator. So initially what we did here was a classical harmonic oscillator. What we now want to do is for n quantum mechanical harmonic oscillators. Okay. So how to do that? What would be the expression for the Hamiltonian of a quantum mechanical oscillator, harmonic oscillator?
Quantum mechanically, I think same expression.
Uh, no.
Just
So, huh?
okay, I will tell. Just just a minute. I think it is same.
Uh,
I think.
So it's not same, because the major difference here is that you don't have the concept of zero field energy right here. So see, it's quantum mechanical. That means the energy levels are discrete now. Okay. So
Uh-huh.
for one quantum mechanical harmonic oscillator, so we can do it, like we can derive and do it, but that's not the scope of the current discussion. But I'll tell you the expression. So for a quantum mechanical harmonic oscillator, the energy levels are given as n plus half h cut
Yeah,
omega.
actually, I know this expression, but I I I think yeah. Okay.
Yeah,
I just
so
thinking that it
huh?
is not okay for that. That reason I'm not telling.
No, no,
Uh,
it's absolutely okay, because so for a quantum mechanical harmonic oscillator, you always get an expression like this, okay? And so this is for one dimension, okay? In one
oh, just
dimension, you have a harmonic oscillator, and that's quantum in nature. So they have discrete energy levels, and this is what you get. And this tells you
uh,
that you have a zero energy, right? Even when n is zero, you get a value of energy that is half h cut omega,
but
right?
it is energy isn't. But I am just telling about Hamiltonian. Just that's why the Hamiltonian
So
will be same.
yes, so normally, so when you if you go at the basic definition of how you define an Hamiltonian for any system, so that is always
Yeah.
given as the sum of the kinetic and the potential energies, and so it's actually the energy. Because see, Hamiltonian is the, so when you use the Hamiltonian operator, what do you get? You get the energy values, right? So Hamiltonian always defines the energy of the system. Okay.
Yeah.
So initially, when you write this expression here, what do you do? This is actually the energy of the entire system. For each particle,
Yes.
this is the kinetic energy, this is the potential energy, and for n particles, you have n of them. So the Hamiltonian of the system gives the total energy of the system. Okay. So
Okay.
what you do here is that now you first find it for one quantum mechanical harmonic oscillator, and then we can multiply by or we can do a to the power n thing for in order to get the values for n quantum mechanical oscillators, right? So what we do here is that now, because the energy levels are discrete, we do a summation. We don't do an integration, we do a summation. And if we do that, we get an expression like this. So here you can see that because this term minus beta h cut omega does into half, this term does not depend on n. So you have taken that out. And this is the summation over n that we get. And then we can just use the geometric series relation to finally get to an expression for the partition function. So is this thing clear to you? How we are doing this thing?
Yes.
Yeah, yeah. So now if you have the expression for the partition function, that is for one particle, and then for n particles you have to the power n. So when can you do this? Is it always okay to use this relation, that you do it for one particle and then you use you do to the power n to find it for the n number of particles? Is it always true, this relation?
It is only for discrete, indistinguishable. Sorry, distinguishable.
See,
Distinct.
uh, no, see. First of all, distinguishable and indistinguishable comes in the calculation of your microstates. So when you
Yeah.
are defining the system, or when you're finding so if you are doing an integration or if you're doing a summation, and there when we have to find the so number of microstates, there you use that relation, that is the Gibbs factor. Okay. But what we are doing here is that we are finding for one particle, and then we are doing to the power n for n number of particles. So we can do that only when the particles are not interacting. That means each of the particles have their independent probability distribution. Okay, they're identical, but they are non interacting. So we do it for one particle, and then we consider that each of the particle will have the same distribution. So we do to the power n. So this is possible when we have non-interacting identical constituents. So here we have n identical non-interacting quantum mechanical harmonic oscillators. Only in that case this would hold. The 1 by n factorial case comes because of distinguishability and indistinguishability, which is the Gibbs factor, which tells you, which comes into the calculation of the microstates when you are defining the partition function in order to include the number of microstates. Correct? Both are different you can say concepts. Is this clear?
Yes, yes. Actually, इससे थोड़ा देर पहले जब हम वो बताए थे ना, तो मेरा गलत हो गया था।
कौन सा?
I, नहीं नहीं, वो इंडिस्टिंग्विशेबल के लिए बताए थे ना, तो उस समय हम बोल दिए थे पार्टिकल के लिए। तो इस
So
बार
you're confusing with, so try to think from like with the reason, and then you'll get the answer. So don't just try to remember, because then you can mess it up. Okay. So in this case, when we were using this 1 by n factorial, or whether we are considering n factorial or not n factorial, there we are actually trying to find how many ways can you have a system with a particular macro variable. So you want to find the number of microstates. But this is a different concept. This tells you that you are finding the canonical ensemble for one particle, but then you want to find it for n particles, and you just do to the power n. And you can only do that if these events are independent of each other and they are identical. This is a probability concept, which so both are probability concepts, but they are different independent concepts. Okay. So so this you can do only when they are non-interacting and they are identical constituents. Clear? Don't forget this, because it will make your work easier. You can find it for one particle and then do it for n particles. Okay. So now once you get the expression for the partition function, uh, so here also see, we do not need any Gibbs factor because we have considered the oscillators to be distinguishable. Okay. So both are different things. You have to first see whether they are distinguishable or indistinguishable, and then you have to also check for whether they are non-interacting and identical, and can you use this relation. Once you do that and you get the expression for partition function, now you can get the expression for the different thermodynamic potentials. And it's interesting to note here that now the value of pressure is 0 here. Can you tell me what could be the physical significance of pressure being 0 here? Any idea?
okay, I am thinking.
Yeah, yeah.
Because it is non-interacting.
No, see, when individual gas molecules are moving, they can move and they can exert pressure on a surface, but even then they can be non-interacting with each other, right? The particles are
Yeah.
moving, they're not interacting with each other, but they go and hit the surface, and then you get a pressure, right?
But it is, I think, harmonic oscillator, and
Hmm.
harmonic oscillator in nature is to and fro.
Yeah, so it's localized in space, right? It's not going, it's not moving and not going and hitting something, right?
Yeah.
That's the reason why you are getting P to be 0. So so what this tells you is that P is 0 because these things are fixed in space, and they don't have this capacity to go and hit some surface in order to exert pressure, right? So that's the relation, that's the reason why pressure is 0 here. Okay. Okay.
Yes.
So now, uh, once you find the expression for the free energy, you can also find the expression for the entropy or the internal energy. And here you can see that this is your 0 point energy, right? n h cut omega into half. This is your 0 point energy. And then you have this expression which has a, so here as you can see, this is the first term is the 0 point energy, and the second term, it depends on, so you can write it as something like this, where the second term can be written as a mean occupation number or mean quantum number expression. Okay, so you can write it as n h cut omega into half, that is your 0 point energy, plus n into this. uh, so this is your mean quantum number. You'll later see that this mean quantum number would change depending on the type of distributions that one can have. And then the expression can be simplified to some, oh, one second. Where is- huh. So the expression can be simplified to something like this. So this is h cut omega into half, and then this value here, which has the dependence of the distribution, the kind of system that you have, or the kind of ways in which a system can be, or the microstates can be distributed in the system. Okay. So now what we next do is we try to solve certain questions based on all the discussions that we have been doing till now. Okay. So you have a system of n non-interacting classical particles, each of mass m in
Network.
two dimension.
I just hello,
Huh.
hello, ma'am.
Yes,
I
yes,
think
tell me.
नेटवर्क इधर का पुअर है, तो मेरा हम डिस्कनेक्ट हो गए थे, तो थोड़ा सा
Oh,
पीछे का छूट गया.
oh, okay. So, what I told here is that, see here, you if you get to that expression for the internal energy, you'll see that the first term is actually the 0 point energy. Okay, and it's n times that for one oscillator. Okay, so for one oscillator, it will be h cut omega into half, and for n of them, it's multiplied by n. And then the second term here can be simplified in a way that we can define an expression for mean quantum number, which is given by this expression here. And then for a single particle, we can write the expression to be something like this. Okay. So here En or epsilon n, uh, it is averaged out. So this is the mean energy for single oscillator, which is h cut omega into half. This is the free 0 point energy plus the mean quantum number into h cut omega. Okay. And then if you have n of them, it will be given as n into this for the single oscillator. So you'll later see that this mean quantum number expression can change depending on the kind of distributions or the kind of phase space densities that the systems or the constituents can have. Okay. So what we now do is we try to solve some questions based on what we were discussing previously. Okay, so here we have a system of n non-interacting classical particles, each of mass m, and it's in a two-dimensional harmonic potential. Okay, so what we want to now do is we want to find the canonical partition function of the system at temperature T. So can you tell me how to proceed with the question?
I think just put the energy of the. Oh, it is classical, no?
Yeah, it's classical.
It's classical.
So for a classical normal, like when we talk about harmonic oscillator, we do it like half kx square, half ky square, right? So it's in two
Yeah.
dimensions. So what would be the changes from the normal discussions that we have had? We have already discussed about classical harmonic oscillators, right? So what would change from that case?
I actually just
So what would be the Hamilton? First we have to go in this way. What would be the Hamilton?
Hamilton is p square upon 2m plus
Hmm.
m omega x square plus y square.
P square upon 2m,
Uh, sorry, px square. Px square upon 2m plus py square upon 2m.
right?
And the half m omega is x square plus half m omega y square.
So here we don't use half m omega, we just use the potential. So that would be plus alpha x square plus alpha y square. We don't know whether it's half m or whatever. That is the normal expression, but the question tells us that it's in a potential given by this expression, right? So the Hamilton will be kinetic energy plus potential energy. Kinetic energy is, as you said, it's correct, p square by 2m plus px square by 2m plus py square by 2m, right? And then plus the potential energy, which is alpha x square plus alpha y square, right? So this is for a single particle. And then for n particles, we have to do a summation, which goes from nu equal to 1 to 3n, 1 to 2n, right? No,
Yeah.
I'm saying it as wrong. See, so we don't have
No.
to do it as 1 to 2n because already we have considered as x and y, right? So it should be from 1 to n, correct? See, when we do integrate summation nu equal to 1 to 3n, we do 3 because it's in 3 dimension. If it's in 2 dimension, we do 2n. But here we have already considered x and y separately. So we have to just do a summation for n particles. So it should be nu
Yes.
equal to 1 to n. Okay. And then we have to use this integral, right? So we have to do the integration over the phase space for for the value of e to the power minus beta h, and in the expression for h we have to use the expression that we just discussed. So we get something like this, right? This is for one particle. Is this
Mm.
clear? We do an integration for px, for py separately, and then we do for dx and dy. So we break the Hamilton for the individual variables. Okay, the h squared term comes because of the Heisenberg uncertainty, right? Now, because now it's in 2D. Is
Yeah.
this clear how we get to this expression?
Yes. Yes.
Yeah. So now if you integrate this, if you try to solve using this relation, what do you get?
Okay.
So it's pretty simple. You have to do some substitutions so that you get this constants out and you just
Yeah.
have something like this. Try solving because if you get
Yep.
used to this
Yeah.
kind of calculations, it will be easier.
Okay. 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 I'm trying. Give me some time.
Yeah.
Can we multiply the constant in with root pi?
Yes. Uh, so you have to do the substitution, take the constant out, and then each of the integrals will have a form of something like this, and then that will be
Yeah.
substituted as root over pi. So the answer might have a, so it would match with better with one of the solutions. There is some constant factor missing, but otherwise it would match with some, match better with one of them, one of these.
Okay, I am unable to solve now because power has gone. I am in dark mode.
Okay, so I guess I'll share the solution. Uh, we have another student here. It's clear, right, for you as well?
Yes, ma'am.
Yeah, okay. Abhiram, it's okay. I understand you're in dark mode. You can switch off your video. Yes, okay. So, what we do is something like this. Okay, we get the constants out and we multiply by root over pi for when we evaluate this integrals. And what we get is an expression like this. Okay, so now this matches better with the option given here. We have a h square missing in the expression, but otherwise it matches better with the expression given here. So this is your solution. The answer is D. Okay, so now let's go to the next question. So here, this is a very simple question. It's just to recap your concepts of finding microstates. So you have n distinguishable particles, and they can be in two states, 0 or epsilon. Okay, and it has a total energy of n into epsilon. That means there are n particles in epsilon state. Okay, you want to find the entropy of the system. So you should be able to answer it just by looking at it. So can you tell me how to proceed with this question?
I think it is G.
D?
Mhm.
Yeah. So why is it D?
Because it has two energy level,
Yes, it has
zero,
two energy levels.
and
So the
some of
question,
the particle is ground, and some of the particle may be in excited.
right. So that means it's the number of microstates, or the entropy is K, L, and omega, where omega is the number of microstates. And then number of microstates will be given as NC small n, right? The number of ways you can uh, take n particles out of capital N number of particles, right?
Yeah.
And that is something like this. So this is your expression for entropy. So it's a very pretty simple question. So similar combination and permutation concepts would be useful if you have to find uh, the number of microstates in different questions. Okay, so now next question. So here we have rotational energy levels of a molecule, which is given by this expression here. Okay, and L goes from 0, 1 to dot dot dot. Now what we want to find is that we want to see uh, the contribution of rotational motion to Helmholtz free energy per molecule at low temperature. Okay, and so we have to find the expression for the Helmholtz free energy, and you have to see how it goes at low temperature. So what would be the expression for the partition function in this case?
Just multiply the 2j, I think 12 plus 1 factor.
Right.
In part, sum of, yeah, okay.
Sum of L equal to 0 to infinity, and then we have
Uh,
12 plus 1. Okay,
into
and
e to
then
the
we
power
have
epsilon.
e to the power minus beta EL. Right.
Yeah.
So it's something like this. Okay, and we get L equal to, the value for L equal to 0, it turns out to be 1, so we get it out. So this is the expression for the partition function. What we then do is we try to find the expression for the
In this, ma'am, in the second, in the last equation, we
Hmm.
just use the L equal to 1 to infinitum, na? Because,
Correct. This should be 1 because
yeah,
already we have considered 0. So 0, it is 1 for 0, L equal to 0 plus L equal to 1 to infinity. So what we then do is we do an, what is the relation for finding the Helmholtz free energy?
F equal to nkt ln omega, I think. Sorry, ln z.
KT ln Z, right?
Yeah,
So
my, yeah.
So that means we have to do ln z. Now here we will use this relation that, see, z is in form of some 1 plus x, right? It has a form of 1 plus x. So we use this expression for ln 1 plus x. And here we only use the first term. It's because we are limited by the low temperatures. Okay, if the temperature is low, that means uh, the higher terms does not remain because we have this e to the power minus 1 by t terms here. So we'll just have the first term. And what we get is an expression like this. So this is your expression for the Helmholtz free energy. Correct? This is clear till here?
Yes, ma'am.
Yeah. So now what do we do next? We get this expression. What do we have to do next? See, this does not match with the expressions given here, right? We have to do something. What do we do? Any idea?
Uh, can we use the expansion of exponential?
Yeah, you can try. Like you can do that. And then what do you get from there? So e to the power minus x expression is 1 minus x plus x squared by 2 factorial minus x cubed by 3 factorial. I guess that's the expression, right? So think of the case that you want to work at you want to get the expression for low temperature. You can
Low
do the
temperature,
uh,
that means T tends to zero na.
so it's not like going to zero. Then though if t tends to zero, then this entire thing goes to like you can do tending to zero, right? So uh, it's a lower value. So uh, think of the summation and think that what remains when you work at low temperature.
Just put the one for L.
So you want to put the first value of L. Why so?
Yeah, I just want to think how equation looks like.
So if you do the expansion, what do you get? If you do the
Uh,
expansion, that's the
yeah,
wave. But what do you get out of that?
okay. Minus 3 to the power.
See, smaller values of t, meaning this value will be decaying very fast, right? Because it has e to the power minus 1 by t. Okay, the smaller the value of t, 1 by t would be larger, so it would decay
I guess
first.
getting the answer D if we put uh, 1 for L, and
Correct.
other order I will neglect, isn't?
Other orders you'll neglect, but the answer is correct. You have to put L equal to 1. But the reason for that is that so you're already in the low temperature limit. So there you want the numerator, you can just work with the first value of L because the bigger the value of T, this will decay faster, right? Smaller the
Yeah.
value of T, it will decay faster because it has e to the power minus 1 by T kind of dependence. Correct. So that's the reason why you choose L equal to 1, right? And you get this expression. Clear? So that's your answer for the third question. Okay. So now this is another question. Here you have the vibrational motion of diatomic molecules may be considered to be that of a simple harmonic oscillator with angular frequency omega. If the gas of these molecules is at temperature T, what is the probability that a randomly picked molecule will be found in its lowest vibrational state?
I think it is C.
Okay. How do you proceed?
Just to derive, I actually we have Helmholtz free energy, and to use the condition of S equal to del F upon del T, like when differentiate with the sign, because we have sin S term, so then okay, I think I am guessing.
Yeah, you are. So, see, you have to use this relation here. Okay. So you want to find the probability that the molecule is found in the lowest vibrational state. So you have to find P I, where I is for the lowest vibrational state. So how you do is, you have energy given by the expression here. Okay. Because it is specified by angular velocity omega, that means the energy levels goes like n plus half h cut omega. So you have to define z by the expression here. So it does not end here, it should be plus dot dot dot, so it continues, right? So that gives you the value of the partition function. Now what you have to find is what is the probability that it's in the lowest state, that is for n equal to 0. Okay, so that means you have to find this expression, right? E to the power minus e of the lowest state is h cut omega by kbt. Okay, one second. Lowest vibrational state. Okay, lowest vibrational state. So that means their n is 1. So I'm just worried. One second. How do you do that? Randomly picked lowest vibrational state. Okay. For lowest vibrational state, they are considering it to be e to the power nh cut omega. Yeah, it's right. So this is the value of the partition function. Now this is the expression, or this is the parameter for the first vibrational state, and that is what you have here. Okay, and then you have to find the expression for this summation. So what you then do is, it's just taking the this first term common and doing the using the relation for the geometric series, and what you get is an expression like this. Okay, so that matches with your option A. So whenever you are asked to find the probability of certain state, of being in certain state, you have to use this relation. So this is for an discrete system. For a continuous system, you have to replace the summation by integration. Is this clear?
Yes.
Yeah. Okay. Okay. So now this is another question. The energy levels accessible to a molecule have energies 0, delta, and 2 delta. Okay. A gas of this molecules is in thermal equilibrium at temperature T. The specific heat at constant volume in the high temperature limit varies with temperature as. So here, uh, the first thing that we have to do is, obviously we have to find the partition function. What we then do is we use the partition function and we see that how we can get the free energy. And then from the free energy, there can be two ways. One is we can use the free energy to find the average internal energy and do a derivative to find the specific heat, or we can see how we can get the expression or the dependence of temperature of specific heat directly from the free energy, right? So first we will find the expression for the partition function, correct? So what would be the expression for the partition function?
Sum over all state like e to the power sum of e to the power minus beta en.
Right. So that means the expression for the partition function would be something like this, right? From here, now if we, so here A is the free energy. So if you have to find the free energy, we get an expression like this, correct? And we have used the series expression for the individual exponentials to get an expression of this kind. So that's fine. We get the expression for the free energy. What's interesting here is that what do you do next? So see, one way is you from the free energy, you can find the individual parameters like thermodynamic parameters, the entropy and the temperature. Uh, yeah, the entropy. And then you can use the relation like F is equal to U minus Ts. So U equal to F plus Ts. So you have to also find the expression for entropy. And similarly, you get the expression for the internal energy. And then like do a derivative with respect to temperature to find the specific heat. But there is a less lengthier way. Okay. So a shorter way rather. So the shorter way is that look at the expression. So this is your expression for the internal energy. Internal energy goes as minus del del beta of ln z. We have already seen that. Now this z can be replaced. So ln z can be replaced as f by kt. Okay, and then we this minus makes this thing plus. So that means u is equal to del del beta of f by kt. Okay. And now if we do a derivative, like if we change this variable from beta to temperature, what we get is this expression here. Okay, because it's like del del T of F by KT into del beta del T. And then you get this expression. So that means that now when you have the expression for the free energy, okay, you can use this relation to get the internal energy. Or what this also tells us is that now if you do a derivative with respect to temperature, you'll see that the specific heat only depends on a term like T del square A del T square, right? So what you have to do is, this is your expression for internal energy. Try to do a derivative with respect to temperature. So what do you get? Try to do a derivative with respect to temperature, right? This is your expression for U. Try to do a derivative with respect to temperature. So see, the first term will be, first is, so if you just, uh, so there are two terms dependent on temperature. Okay, so one can be like minus k t square, and this has 1 by t. So it should be minus 1 by t square del into f, right? And then t square gets cancelled, correct? So I guess, okay, either I have to write or I have to show otherwise. So the main fact, I'll show the solution and then you'll understand. But the main thing is that, see, here you directly get an expression of internal energy and the free energy. And it depends on temperature. And now if you do a derivative with respect to temperature, that directly tells you what's how the specific heat depends on temperature. You don't have to do all the calculations of the different entropy and all other expressions. Okay. So you have to find del A del T and you have to find del square A del T square. And you'll see that this is what you get. Okay. So this is your del A del T. This is your del square A del T square. Okay. And then the CV, so A is actually F, okay, the free energy. And the CV then only depends on minus T del square A del T square. So that means if you have the expression for A, just do a double derivative with respect to temperature, okay, and multiply by temperature, and that would give you how your specific heat depends on temperature. Is this clear?
Ma'am, can you please explain once again?
Yeah, okay. So see, what I meant here is that this is your expression for the internal energy. Okay. So now you have to find how Cv depends on temperatures. That means you have to find del U del T, right? So if you do del U del T, what do you get? Try to do del U del T and see of this term. That will tell you the solution, like what's the expression. So see, it's minus KT square. Okay. Now in that you have this, this is your expression for F. So what you can now do is you have to take the 1 by T term out. So it should be, you can take 1 by T out or 1 by KT out, and then it should be del square F by del T square, right? Or otherwise, what you can do is you can do a derivative of this T here also, right? And then it will, this will cancel out because 1 by T derivative will be minus 1 by T square. So then these two terms will cancel out. Are you understanding?
Yes, ma'am.
Yeah. So when you do all that, like if you do that expression, and then you have to use also use this high temperature limit. That means, see, in the high temperature limit, this term becomes constant. Okay. So in the, there it just has this dependence because high temperature meaning this term is very small, and ln3 it would be just be a constant. So it has a linear dependence on temperature. So then if you use that relation, what you will see is that del U del T or the CV just goes as minus T del square A del T square or del square F del T square, where F is the free energy. Okay. So that means if you have the free energy that you already have here, you can directly do a double derivative with respect to temperature and multiply by temperature to get how Cv depends on or varies with temperature. You don't have to individually find the expression for pressure or entropy, or and then use the relation that F is equal to U minus Ts, then find the internal energy, then do a derivative. You don't have to go through that entire process. Okay. Directly from the free energy, you can use this relation to see how it depends on temperature. Is this clear?
Yes, ma'am.
Yeah. Okay. So now let's look at another question. So a particle is confined to a region of x greater than equal to 0, okay, by a potential which increases linearly as ux equal to u naught x. We want to find the mean position of the particle at temperature T. So how do we do this? What should be the process? So what do you mean by the mean position? What, how do we find mean values?
Mean in the sense of expectation of x.
Yes. So if you say mean of position, how do you plan to evaluate that? So mean means if you have some probability distribution P of x, how do you define mean of x?
I just use the u naught x in the probability distribution, I think.
No, so it's fine. You have to use the expression of u naught x in the probability distribution. I am saying you have the probability distribution. Think that you have already got the probability distribution. How do you find the mean position?
Just a derivative with respect to x with probability distribution. I think I
Why?
know. I have no idea.
No, why? See, you have to think with reason. Why do you say that you will be doing a derivative? Derivative is not needed, right? What do you mean by mean? Mean is like an averaging kind of concept, right? You just said it's like expectation value. So,
Yeah.
given a particular probability density, if you have some variable x, and if you know the probability density of that variable x is given as p of x, how do you find the mean of x? So that this is a pure probability concept.
No idea, man.
So see, uh, when you define moments or when you define each of these values, what you do is you do expectation values of different powers of the random variable. So when you say mean value of x, that means you are doing an integration of x into px dx, right? So it's like, what is mean? If you have five options, so if you have so given you have 10 variables, 1 2 3 4, so how do I explain? So you can have any numbers between 1 to 10, okay, and you choose five numbers. Now what would be the mean depends on, so if you choose these five numbers and then you get maybe 3 for 3 times and 2 for 2 times. So how do you find the mean of your expectation? So what you do is you do 3 into 3 plus 2 into 2 divided by 5, right? Something like this. Or you add all the outcomes and divide by the number of outcomes to get the mean. So that means what you are doing is you are multiplying the probability of the individual outcomes, and you're doing it for all the possible outcomes. So here your thing is a continuous variable. So that means if your variable is x and the probability density is p of x, the mean is given as integration of x px dx over all the values of x. Is this thing clear? This is the basic concept of finding mean. You can say basic concept of probability, statistics, and like everything. Is this concept clear?
Yeah, concept is clear, but I have forgot the all formulas like Coleman's mean.
Hmm? I lost you. What did you say?
Yeah.
So see,
I
the, the, yeah, tell me.
I think I have forget the all formula of
No,
probabilities.
think just don't think it like a formula. Think it like think about the concept behind. You want to find
Yeah.
the mean of some value. So in uh, so suppose you have five outcomes and each of them is 1 2 3 4 5. So what do? You do 1 plus 2 plus 3 plus 4 plus 5 divided by 5. That is your mean, right? So here what are you actually doing? Your 1 comes one time, 2 comes one time, 3 comes one time, 4 one time, and 5 one time. So each of them has a probability of 1 by 5, right? So what you are doing is, so you are trying to, so that's the discrete expression, right? Do you understand what, are you understanding what I mean? Think of the concept. So when you are finding moments, each of the moments, suppose you have to find the mean of x square. How do you do it? It would be x square px dx. If it is x cube, it would be x cube px dx. That's how you find the expectation value of any uh, observable quantity, right? So that means the question here is to find the mean position. So you have to find integration of x px dx. Now you don't know the value of px yet. So in order to find the expression for px, now you have to use the, the, the knowledge about the potential that is given here, right? So so what we do here is, this is your value of z. This is your partition function. And this is the expression for the mean position that I was talking about. Okay, x px dx. Okay, and then, so here, like dx and dp, it's coming because now it has both position and momentum. For a single variable, it would just be x px dx, because it's actually the question, or the physical question is to find the mean position, and there it has dependence of both. So you have to integrate over all values of momentum as well. So then comes the expression for dpx here. Okay, if you had just a variable and you have to just find the mean, it would just be x px dx. So what we do is that then we calculate this integrals, and there you'll see that now your potential has this x dependence. So you get that, so that you separate out the x and the momentum parts. Okay, and then this is what you finally get. So obviously you have to practice, or you have to try solving the integrals, but then these concepts are very fundamental, so you should not forget this. Is this clear?
Yes.
So suppose if you were asked to find the mean position, suppose if you were asked to find the mean, uh, let me tell you, maybe the mean variance. So what do you do then? So then you have to use the relation of, so you have to find x square also, right?
Okay,
Then you
okay.
have to use the,
I am on. Okay. The variance is mean of x square minus x square of mean.
square
The
of,
variance is.
right. So it's mean of x square minus square of mean. Very good. So this is your variance. So how will you find that? So you have to first find the mean of x square, right? So how do you find mean of x square? Like just
Mm,
looking at the expression, what changes will you do?
just do the just write the x square instead of x, and the same procedure will follow.
Right. So that will give you mean of x square. Then you have to
Yeah.
also find the mean for x, which is already given here, right? Then you have to do a square of that term and then subtract from the mean of x square, and that will give you the mean variance. Correct?
Yes.
Right.
Actually, I have always remembered the variance, but not the basic. I think this is a problem. But
Yeah, this is a problem. So the problem can be solved by thinking it in terms of reasoning. Like, what do you mean by mean? Whenever you're talking about some mean, you're talking about finding the expectation value. You have to think of how are you doing. So what does it mean physically? It means you have to do this. So it takes into account how things are distributed over the probability distribution. So it has to have either summation or integration over the probability density along with your given whatever mean you have to find, right? So this kind of questions can be very simple and like this is a pretty fundamental concept, so you should not, nobody should forget this. Okay, so now let's go to the next question. So we have a system of n non-interacting spin half particles which is placed in an external magnetic field H. The behavior of the entropy of the system as a function of energy is given by, these are the four options. Okay, so what do you think should be the solution? So I can just say that if you have seen the last day's class, that would tell you what this should be. But even then I'll discuss, but try to think of how to address this question.
It should be MM.
Okay, why do you say so?
Actually, it is a standard problem of magnetic field behavior.
Yeah, okay. So you know the solution, that's fine. But how did you get to the solution? What is the concept behind it? It's not a question for just being in magnetic field. It's actually true for any two-level system. So if you have to think of, so you can find the expressions, and what you have to do is you have to first find the number of phase or the number of microstates corresponding to a particular value of energy, and then you have to, once you get that, so you get the number of microstates in terms of energy, you have to find the entropy, okay, which is given as S equal to KLN omega. Omega is the number of microstates. So I have not shown here the complete solution, but it looks something like this. So this concept comes from the one, from whatever I have discussed in the last class as well. But what is interesting and what would directly tell you that this should be a solution is that in two-level system, we can have regions of negative temperature. Okay. So which means that we can have regions of negative slope, okay, where del S del E is negative. So that is one thing. And second is the expression for entropy is symmetrical about E. So if you remember these two things, you can just directly look at the picture and tell that this is the correct answer. You should do not have to always derive the entire solution, right? And the reason why in two-level systems we have this negative regions of negative temperature is because now you have a limit to what the maximum energy can be, which is not the case for situations where the particles can take any energy, right? And I have also discussed it in the last class as well, so you can go through the discussion. But this is something which is very uh, common, and one should remember this. Remember in the sense understand and remember. Okay. So I'll go to the next question. Is it clear?
Yeah.
Yeah. Okay. Okay. So now uh, we have a gas of n non-interacting particles in thermal equilibrium at temperature T. Each particle can be in any of the possible non-degenerate states, 0, 2 epsilon or 4 epsilon. Okay. The average energy per particle of the gas is. So can you tell me how to proceed with this question?
We will write first in partition function. Then
Okay.
find the
Then what do you do?
then we will find Helmholtz free energy.
Okay.
Then find the internal energy of the system. It gives the average energy.
Okay. And then divide by n to get the individual values,
Yeah.
right? Okay, so that is a valid way of addressing this question. But according to what I just discussed regarding mean or averages, can you tell me in this regard how to address this question? So what you have to find is the average energy per particle. So what does that mean? What do you have to find? So if you get Z, which is your partition function, what is the probability of being in the state 0? What would be P of 0? You know what is Z, right? Z would be e to the power minus beta 0 plus e to the power minus beta 2e plus e to the power minus beta 4e. That is your Z, right? Like you're doing it for one particle.
Yes.
So yeah, that is fine. So you find Z. Now what is the probability of the first of being in the first state? So P of 0. What would be P of 0? Anybody? Like I actually don't know your name. B372.
Anushka.
Oh, hi. Okay. So Anushka, do you have any idea? So if you remember, P of I is equal to e to the power minus beta ei by Z, right? Do you remember that? So I'm talking about this relation. I always have to go back. Huh. So I'm talking about this relation, right? So if you, so this is what we did in this question. We wanted to find the probability that it is in a particular state. So now I'm telling you, if we go back to our question, what is the probability that we probability of being in the zeroth state?
Probability in the zero state, na?
Hmm.
It is one upon sum of the partition function. I think partition function.
One because e to the power beta e and e is 0, right? So e to the
Yeah.
power 0 is 1 and 1 by z. Correct.
Z.
Right. So then what should be the probability of being in the state 2 epsilon?
Uh, it is e to the power minus 2 beta epsilon upon Z.
Correct. And similarly for the 4 epsilon part, right?
Yeah.
Now, what is the average energy? So, what do you mean by, because now you have to find the average. So, what you have to then do? You have to multiply the individual probabilities with the energies, right? So, what did you do when you had to find the mean displacement? You did x p x dx, something like this, right? Because you have to whenever you're finding expectation values, what do you do basically is you have to multiply the probability with the corresponding values. So here what you have to do is you have to multiply the energy of the individual states with the probability of being in that state. Is this clear?
Please explain again, ma'am. Uh,
So
how
so
to
when yes
the
so
average
so
yeah.
so when you have to find any average, so when we were finding average of position, what were you doing? You were doing integration of x px dx, right? So that means what you are actually doing is you are multiplying the value So you have to find the mean of some parameter. What you are doing is you are multiplying the value of that parameter with the probability of being in that value, right? So here what you have to do is you have to multiply the energy with the individual energies with the probability of being in that energy state. So that means what you have to do is, if this one is E1, this is E2 and E3, you have to multiply E1 by probability of being in the state E1 plus E2 into probability of being in the state E2 plus E3 into probability of being in the state E3. And that gives you the mean average. Is this clear?
Yes, ma'am.
Yeah, try solving it.
We just multiply 2 epsa and the average, sorry, 2 epsa multiply with e to the power minus 2 epsa, like,
Okay.
because the average energy particle of the gas. Okay.
So
I think we
the
just
if you
sum up
have
all
to,
the
huh?
okay. We
Yeah,
just
yeah,
sum up all the energy with the individual probabilities, na?
right.
This give.
So E1
Okay.
into P of E1 plus E2 into P of E2 plus E3 into P of E3,
Yeah,
because
yeah,
these
yeah.
are
I get.
discrete systems.
Yeah, yeah. I actually, okay. I have other idea, but okay.
Okay, so you can tell the other idea, but first try to solve it and see if it
I get
matches.
idea. I had solved this type of problem in quantum mechanics to get the average
Okay,
energy, like total energy.
okay.
How to multiply probability with the individual uh, energy to get the total energy. The same idea.
Yeah, so
Uh, working
exactly the
here.
same. So obviously there you're finding the expectation value of energy. Here also you're
Yeah,
finding the average energy, meaning, so these are all physically the same.
yeah.
So that's what you do when you find the mean of a particular of any random variable. You multiply by the individual probability. So when, and now if it is a, so here it's a discrete system, but if it was a continuous system, how will you have done that? It would be energy into P of energy into, you
First
have to do
term
an
is
integration.
zero now, I think.
Yeah, right. First term is zero. Okay. So what is this? Try
I'm
solving it
going.
and tell me the solution. Anushka, you are understanding, right?
Yes, ma'am.
Yeah. Okay. So try solving. I guess you have to do some simplifications. So
I am. I think the denominator term goes to the partition function, and how to solve.
so you will get a number of exponentials, and then you have to simplify them, like expand and
Uh,
simplify.
2 epsi to the power minus 2 epsa plus 4 epsi to the power minus 4 epsa upon z.
Right.
And
And then See, here it's given beta e is less than 1. So that means you can expand the individual exponentials, okay, and then simplify.
Okay.
Hello? Oh, okay. Should I share the solution?
Yes, it takes time more.
Yeah, okay. So what we are doing here is we are expanding each of the terms, okay? And then it's just mere simplification, which gives us the result as 2 epsilon. Is this thing clear?
Yes.
Okay. So the next question. Here, a paramagnetic system consists of n magnetic dipoles. Each dipole carries a magnetic moment mu, which can be treated classically. Okay. Now, in the system at a finite temperature T, and it's in uniform magnetic field H, find the induced magnetization in the system. Okay. So, induced magnetization meaning you have to find the expectation value of mu cos theta, because where theta is the angle with the magnetic field. So how do you do that? So I'll share the solution, but what's the basic idea? So when you are asked to find some parameter, so what do? The induced magnetization in the system.
First, we derive the partition function.
Okay.
Then use the relation of you use the relation of magnetization with Helmholtz energy.
Yeah, you can do that. Yeah, that's okay. But then what you have to see, you can always follow that procedure of finding the partition function, finding each of the, so finding the free energy and then each of the parameters. But then that makes the thing lengthy. What is the easier way is to look at what exactly are you supposed to find. So you are supposed to find the induced magnetization in the system. So that means you have to find first the mean magnetic moment. So when you find the mean magnetic moment, it's given as mu cos theta into, here x is mu b by kt. So you'll see how it's defined here. I'll tell you. So it's mu h by kt. Okay, so that's just a variable that they have taken. But then what you are finding actually is you're finding the expectation value of the magnetic moment or the mean magnetic moment. Okay, and d omega is the it's the steradian, so you can write it as sine theta d theta. Okay, and then integrate. So it's basically the same concept. You're finding, you're doing integration of x px, like x, if x is your variable, if this is your variable, or you can say this is your variable mu cos theta, and then this is your this by this integration is actually your partition function. And then what you are doing is you're multiplying by the individual probabilities, and then this is what you get. So it's similar to what you were doing in order to find the mean position. So here you are finding the mean moment. Is this thing clear? But then because it's in a field, and then you have to consider the angle with the field, what you're doing is you're considering as u cos theta, and you do it in spherical coordinate system. That's the only difference. Okay. And then once you find the mean moment, what you have to find is the magnetization. and you have n dipoles. So what you do is n into the mean dipole moment for one, mean magnetic moment for one dipole. And so this is your induced magnetization. You don't have to go through the entire process of finding the partition function and then give free energy and all of that. You can just directly use the expression. So this already has the partition function, but what you're using here, what the concept you're using is you're multiplying the probability density, or the phase space density rather, with the variable whose mean you want to find. Is this thing clear?
Yes, ma'am.
Anushka, it's clear?
Yes, ma'am.
Yeah, okay. And then when you have to find heat capacity at constant H, so here what you do is you do the derivative with respect to internal energy, and this is the expression that you see. So in a hydrostatic system, we define the heat capacity in some way which has pressure and volume, right? It has enthalpy. And in this case, now it's a magnetic system. So there the heat capacity has an expression like this, okay, because it's at constant H. And then you get an expression like this. So once you find the M, you can just do a derivative with respect to temperature to find the expression for the heat capacity, right? Okay. So let us go to the next question. Now, this is another question where we have gas molecules of mass m, which are confined in a cylinder of radius r and height L. Okay. And they are kept vertically in Earth's magnetic field. Now, we want to find the average energy of gas at low temperatures. So, what do we have to do here? Like, I am not asking you to solve it because it would be lengthy, but what is the process? So again, here you have to find the
But
average. Tell me.
yeah, so the energy will be like gravitational potential will be added
Will be added.
uh,
So talking
in
about the
energy.
Hamilton. So in the Hamilton
Yeah,
expression, you'll have the gravitational potential.
yeah,
Yeah, okay, right. So that will help you in, so that will be used in finding the expression for partition function,
yes,
right? And then when you have to find the average energy, that means you have to do an integration of energy with the phase space density, right? As we were doing in the last case, we did an integration of the mean moment of the magnetic moment with the phase space density. Here we will do an integration of energy with the phase space density. Okay, so let's see how. So this is your expression for the partition function. Okay, now as you said, for free, so this is your momentum dependence, px square, py square, and pz square by 2m. Okay, and then we have dx dy. Okay, and then in dz we have to include this potential which depends on on z because of the gravitational field. Okay, that gives you the expression for the partition function. Now what you do is you can find the expression for z. Okay, and then this is for one particle, and then you can do it for n number of particles. That would be z to the power n. Excuse me. So what we then do here is that, see, what you have to then do is you have to find the average energy of the gas at low temperatures. Now this is the relation that they have used, but how they have got to this expression is the integration of energy with respect to the phase space density. So if you do an integration of energy with phase space density, you'll find that it can be written in terms of the formula that is given here. Okay, so this tells you that if you now have the partition function, you can directly use the partition function to get to the average energy. Okay, it's the same as, so minus del del beta of ln z, and now in terms of rather than doing a derivative with respect to beta, you are doing a derivative with respect to temperature. Okay, and then that gives you this answer. Is this clear? So this in a way tells you that have if you know the partition function, you don't have to do all the, you don't have to find all the thermodynamic variables. You can just use this relation to directly get the average energy from the partition function. And this relation comes from the fact that average energy is defined by the integration of energy with respect to the phase space density over the over the entire phase space volume. Is this clear?
Yeah, yes, ma'am.
Ma'am, in final exam, will we be asked these type of questions, or are we just doing this for like practice?
So, see, basically, I actually don't know what kind of questions will be asked in your exam, because so this TA sessions are basically just to have some problem solving, like develop some problem solving skills and share or discuss your doubts. But then I think you have to ask your instructor directly about what kind of questions might come in your exam for the course. But this is a independent session where we so what I'm trying to do is, so you might be in different exams that come in later time, you might have to solve this kind of questions, and these are based on what has been taught or is being taught in your class. So I thought it would be okay to share this kind of questions and see how this problem solving skills can be developed. But then I literally don't know uh, how your questions might come for your exam of the course, so you have to consult the instructor for that.
Okay, ma'am.
Yeah. Okay. So now this is another question. So here we have a system of n classical non-interacting particles, and then they are confined in an external potential, and you have to find the internal energy of the system. So how do you plan to proceed? The same way, right?
I
You have to,
uh, the answer is B.
the answer is not B.
Um,
Why do you think the answer is B?
then the answer is A.
Okay. So it's either you get a point or you get a negative mark. So what is telling you that the answer will be any of this and not this?
It is the function like harmonic oscillator problem. Classical
Exactly.
one.
So it's not like a harmonic oscillator, it's actually the harmonic oscillator problem.
Yes. Okay.
So just look at the question. The question talks about n classical non-interacting particle. So that means their kinetic energy will be like px square by 2m, py square by 2m, pz square by 2m. And then they are in a external potential, which is given as v of r equal to half a r square. That means it's half a x square plus y square plus z square. So it's similar to writing the potential as half k x square plus half k y square plus half k z square, right? So it's basically a three-dimensional harmonic oscillator problem. So in this case, so it's important to look at the question and be careful about what the question is asking. So that means obviously the answer is A. And how do you get that? You can directly get it from the equipartition law, right? So there is half kT for each degrees of freedom. So for each particle, so along x, there is a potential energy, there is kinetic energy. So half kT plus half kT, it's kT in one dimension. Now you have 3D, like x, y, and z, three dimensions. So that means for one particle, it should be 3 kT. And there are n such particles. So that means it should be 3n kT. So the answer is A. And what this question actually hints at is that, yeah, read the question carefully, because often such questions can come where you might spend a lot of time doing the entire calculation, but then the answer might be very trivial. And you can directly get it from your knowledge of equipartition energy or such fundamental knowledges. Okay. So this is how you do it. So you can do the partition function, you can find the internal energy in this way, but you can directly also do it by using the concept of equipartition energy. Is this clear?
Yes.
Okay. So it's not 3 by 2. Okay. It's 3n kBt. And you understand why it's 3n. It comes from the equipartition as well. Okay.
Yeah, average is the average is the KT. Yeah.
In each, for each coordinate, it would be kT. In three dimensions, it would be 3 kT. And then for n particles, it will be 3n kT. But obviously, you can also follow the normal procedure of finding partition function and then the internal energy and follow this process. But that would be lengthy. Okay. So now this is another question. Here you have a system, and it has three energy levels, 0 and plus minus epsilon. Okay. And the 0th level is doubly degenerate. Okay. And others are non-degenerate. That means, what does this mean is that there are two energy levels at E equal to 0. Okay. And then the average energy at inverse temperature beta is given as what? So how do you plan to do this question?
First, write the partition function, and I think the answer is B, ma'am.
Okay, so I have to check what is the answer, but
Yeah.
uh, how do you proceed? Just don't think
Uh,
of learning the answers by looking at the questions.
no,
Think
no,
of
no.
how to proceed.
Okay.
So what's the
First, write
concept?
partition function.
Okay, so that that
Then,
that huh, then
just write the. That means the derivative with respect to beta for the KT square del L z upon del beta, na?
okay, yes, you can do that.
Okay,
But
okay.
then,
I am
but
doing.
this
Please
is
give me.
but just for your like, let me tell
Okay,
you
I'm
that it's
saying.
a it's a discrete
Just
system.
I am solving, ma'am. Please give me time.
Yeah, okay. Anushka, what do you think? Like, are you proceeding in the same way? What is your take on addressing this question?
And I'm doing it that way only.
Okay.
Ma'am, the energy is doubly degenerate. Then I'm not. I getting two factor, but in option there is no any two factor.
So the zeroth energy is doubly degenerate means there are two such levels. So
Yeah.
answer should match with one of the solutions, but so I have to. I'll discuss the solution once you have tried.
Okay, ma'am. Uh, I am solving.
Okay.
I am getting C.
Okay. And what is Anushka getting?
No matter
Ma'am, see.
Okay. So now let's see how what the solution comes out to be. Okay. So here, this is how you get the partition function, right? So here, what you have considered is this GI is your degeneracy factor. So when you consider two states for equal to 0, you get 2 into e to the power 0 plus these are only these are non-degenerate, so they are e to the power beta e plus e to the power minus beta e. So this is your expression for the partition function. Okay. Now what you have to find is the average energy. So what you do minus del beta of ln z. Okay. So if you do that, this is the expression that you get. Okay. And with some, there's a certain simplifications that they have done. So this is a sine term and this is a cos term, sine hyperbolic and cos hyperbolic, and that gives the answer to be A. Sorry, not A. Is it A? No, it's D. Yes. So can you check where your solution might have gone wrong?
Yeah, just okay. For sudden solution, I made a mistake on e to the power minus beta epsilon.
Okay, so it's
Okay.
a calculation mistake, right?
Yeah.
But yeah, but this is
Um,
a
the-
normal. The process is
I
correct,
was,
right? There's no
just I made a mistake on the just assume the both of the energy will be same positive. That's why I'm getting zero.
Oh, okay.
For the
But
sudden solution, it's my fault. Okay.
yeah, exactly. So the concept is clear. So you can see your calculations. It should be plus
Yes.
minus epsilon. Yeah. Okay.
Actually, today I have made more mistake just solving, trying to guess in every problem. Okay.
Yeah. It's okay. So like this is the basic way of solving for the average energy if you are given if you know the partition function. Okay. So Anushka, you could understand where you did wrong, right? From the solution.
Yes, I made mistake while calculating the E.
Okay, 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 okay. So,
Yeah.
okay. So, this is another question. So here, because for the sake of time, let me just discuss the solution with you. So here you have a collection of n non-interacting spins, okay? and they're kept in external magnetic field B. So this is the Hamiltonian. Then what should be the minimum value of mu B by kT for which the mean value of SI is greater than equal to half, one third. Okay. So let's see how we do this question. So similarly here, so similar to that case where we had individually found the probabilities of individual energy states, right? 2 or 3 questions back. Similarly here, define the probability for individual spins, okay? Spin +1 and spin -1. So what is the mean spin value? So it should be S1, that is +1, into P of +1 plus -1 into P of -1. Okay. So this is what they have done here, and that gives you the mean value of spin. Okay. What is told here is that what is the value of mu by kT for which this is greater than equal to one third. So then just you have to, obviously it's for one spin, and then for n spin you have to multiply by n, and then you have to use this relation, and that gives you the value of mu v by kT. Okay, so the answer is C. But what's interesting here is again, and what is more of more fundamental importance is how this mean value of spin was found. Okay, so it's similar to how you had found the average energy 2 or 3 questions back, right? So this is clear, right? The solution is clear.
Yes, ma'am.
Okay. Now this is another question where there's a gas of non-relativistic classical particles in one dimension, and then they're subjected to a potential. Okay, and then you have to find the partition function. So it is a pretty direct question. You know the potential, so you know that you have to include this in the expression for the partition function. Okay, so this is how you do the expression. Obviously here you have 1 by h because it's in one dimension. Okay, and then you separate out the momentum and the position terms, and then on solving the integration, this is what you get. Okay, so if you use this relation and do the integral and then use this relation here, so this is the answer that you get. So these are pretty standard questions where the potential is given and you have to find the corresponding partition functions. Okay, and the next question, so this is a very standard and simple but standard question, is that your Hamiltonian is given in terms of a matrix here, and now you have to find the partition function. So how do you plan to proceed with this question? Any idea?
Just put the exponential term e to the power minus beta h and use the properties of exponential of matrix.
Okay, so you can do that, but that would make it difficult because now it's not a, so it has four.
Okay,
uh,
so the another process is just find the eigenvalue of the matrix and find
exactly.
the uh,
So if you do the eigenvalues, that means you are actually getting the values corresponding to the two energy levels, right? So that means
yes.
that would bring it down to a question where you have two energy levels and the energies are known to you, and you want to find the partition function. So that is far more easier than doing it using the properties of matrix. So if you do that, the eigenvalues will turn out to be this, and then you can just directly use this relation, and that would give you this value. Okay, so this is your answer would be B for this question. Is this clear?
Yes.
Anushka, is it clear?
Yes, ma'am.
Okay, so this was all. I tried to discuss some of the questions regarding canonical ensemble. So that's it. I'll meet next Monday. Okay, so Thank you.
Ma'am, can
Yeah.
you please share the link of the YouTube channel on which you'll be uploading this video, because they update the Excel sheet containing the links to the videos much later.
Oh,
So
okay, okay.
if
I
you
thought it
share
was already
the
shared. Uh,
no, they have shared the link to the sheet, but it gets updated like much later.
okay, okay. So one thing is that when you end this meeting, even in Teams, you'll get this recording being saved. So you can download it directly from there as well. So do you understand? Like when this meeting will end, you're doing it in Teams, right?
Yes,
Uh,
but it would be much easier to, for the
so
YouTube.
yeah, I know, but how do I share it? So what if I share it on so then I'll have to share it on the next class. Like how do I contact you then? That's what
No,
I was
what
thinking.
I'm saying is, uh, the recording which you are going to put on the YouTube channel, and then that
Hmm,
link you would put in the Excel sheet, correct?
correct.
So if you just share the link of the YouTube channel in the chat box, then we can directly follow you
Oh
all
yeah, 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 yeah.
in the
Yeah, yeah, I
previous
can do
videos
that.
also there.
Yeah, I can do that. So I'll share the link in the chat box of the Teams, right? That would be fine.
Yeah, the channel link, yes.
Yes. Okay. Okay. Yeah, I'll do that. Okay. Okay. Thank you.
Okay, ma'am.
Yeah. Thank you.